A lot of people ask me how to approach a new problem and solve it during the contest. To help you improve your problem solving skills, I have decided to start this CF reflection series where I will take a look at the notebook that I used during the contest and I will walk you through the thought process that I had to arrive at the solution. Consider problem D from Codeforces round 968. You are given several lists of integers and each list can contain multiple integers. You are also given an initial value x, and in one operation you can select any of these lists and update x to be equal to max of this array. And what is this array? It is nothing but this initial list combined with the number x. You can do this operation as many times as you like, but there is one easy version of this problem where it is allowed to select one list more than once, and there is a hard version of this problem where you can select one list at most once. Then they define a function called f of x, which is equal to the maximum value that you can achieve when you start with the initial value x, and you need to compute the sum of f of I, where I ranges from 0 to m and m can be of the order of 10 to the power 9, and so can the values of the array elements. Looking at the constraints, my first thought was, if m can be of the order of 10 to the power 9, it is of no use to compute f of I for all I, because we will not be able to compute those in time. However, from my previous experience with max based problems, I knew that by the pigeonhole principle, max of a list of integers cannot exceed the size of that list. Therefore, there can be only two possibilities. Either we do not apply any operation on that x, or we do apply at least one operation. But if you do apply at least one operation, the final max or the final x would have the format equal to max of some list, and we know that the max of any list cannot grow beyond its size. Therefore, it is clear that the answer cannot exceed the maximum length of any of the list plus 1. And then it became quite clear that this function f should follow a pattern where it needs to be some value and after a fixed point, and that fixed point is equal to the maximum length of a list plus 1. After that point, it is optimal to never apply that max operation anymore, because the answer would decrease. So this would be the pattern, and it is clear that the only sensible f values that needs to be calculated are till f of maximum length of the list, which is bounded by 2 into 10 to the power 5. So now it gave me enough confidence to explore the approach of fixing one x and finding the value of f of I. Now I decided to select a random list. Suppose this is the random list, and there can be two cases. Either I do not provide the max, but if I do not provide the max is the first gap in this array that is missing. So this will still be missing because you did not provide this element. So no matter you provided this section or this section, this is still missing. So the output would be equal to the max of this list. But if you decide to add this element, that is, you decided to fill this gap, then it would return the second gap. So if you decide to provide max, it will give you the second missing element of that array. Now it is natural to think that, can we provide the second missing and get the third missing and repeat this process? So I tried that, but you will notice that if you provide the third missing, then this gap will still remain, and that means that the answer would still be max of list. Therefore, no matter how many operations you do on a list, the best outcome that you can get from any list is equal to the second missing element. However, this best outcome will only be achievable when you provide the input as max. But when you write down these two equations on paper, you will see a very nice pattern. So the output of the first operation is max, and then you can pass it as an input to get the second missing element. And very naturally, since the problem says that you are allowed to use one list more than once, you can do this operation on any list twice to get the best outcome from that list. So in a sense, when you start with X and you start with this list will take that X, and if you do that operation 2 times, it will promote that X to the second missing element of that list. And that is the best it can do no matter what X you start with. So then it is pretty clear that every list can provide you the best value of the second missing element from that list. So you take the maximum of all of these second missing element, and that is your answer. Why is that your answer? Because we just showed you a way to achieve that second missing element by doing the operation twice on the selected list. So this is the code. You iterate through all the list, and since now notice that the array elements, it can be of the order of 10 to the power 9, but from pigeonhole principle we know that at least one element from 0 to length would be missing. So we track which elements are present, and the first element that is missing and the second element that is missing, we track those for each list, and then we figure out the maximum. Once we figure out the maximum, we know that we have found this point, right? The second maximum will go till this point, and after that it is optimal to not use the max operation anymore. So then you can use the formula of sum of natural numbers to compute this sum, and then this sum is simply Sm multiplied by the count of numbers that you have over here. So I have written a utility function to compute the sum of n integers, and then I use it to compute the sum of a range. In the hard version of this problem, you are not allowed to use one list more than once. But notice that whenever you had the freedom to use one list any number of times, the best you could achieve is the second maximum. So now with some restriction, of course the best that you can achieve cannot be greater than this number. It has to be less than or equal to this number, and your goal should be to achieve it if it is possible. Now notice that the previous algorithm was to use one list twice, that is add any input over here, get back max, then fill in this gap and get back the second max. But now they are preventing this feedback loop, that is if you have a list, you cannot provide the output as the input again. Therefore they want you to get the output from some list and then pass it to some other list input. So it is natural to think of neural network and graphs, because that is how it works. The output of one layer is equal to the input of the other layer. Now notice that if you provide this max to this list to fill this gap, you will get back the second max. So for a list, the only thing that matters is the value of the first missing element and the second missing element. So let us create a graph where we will say that if you provide an input 2, it will lead you to the output 7. So 7 is the second missing element. Now we need to figure out how can we get the maximum value node on this graph, and that would represent the maximum second missing element of any of the list. Now notice that this graph will always be a DAG, that is it is a directed acyclic graph. Why? Because any edge starts from M and goes to Sm. So M is the missing element that will be strictly smaller than Sm. So this is a directed acyclic graph, so you can perform dynamic programming on it if you want in the reverse order, right? Now you can think of this as railway routes. So if you start at station 2, you can reach these stations, right? So now if I want you to travel any of these paths in this graph, what would your final destination be? You can notice that the final destination would be equal to the best second maximum element that you can achieve. So you can traverse this route over here by providing the output of one layer to the input of another layer. But what if you want to travel this route but you are not currently standing at this station? in that case, recall that if you do not pass in the max to that function, it gives you back that max. So it is like teleporting to a station, but teleporting will only be possible if you sacrifice this particular edge to use it as the teleporter. So suppose if you are standing at point 23, using one teleport you can go from 23 to 2, but that would mean that you will not be able to use the list that provided you that jump from 23 to 2. That would mean that this edge will now get invalidated. Therefore, you can see that you can travel any of these edges, you can walk through any of these routes as long as you can teleport to it. So now, since it divides the problem into two sections, that is whether you started your journey before the teleportation or after the teleportation. So then you can define in dp of u and out dp of u. So in dp of u would indicate that what is the last node that you would reach when you do your journey starting from this node and you only travel to the next higher node. So what is the last node that you would achieve? And populating this is pretty simple. In dp of u would be equal to the maximum value of the in dp of children, right? So you can fill it in the reverse order, reverse topological order. Now what about out dp of u? So remember that out dp of u means that you still want to traverse this same route, you still want to get the benefit of that result, but you want to use one operation to teleport from wherever you are to this node, because remember that out dp of u represents that you are somewhere else in space and you want to reach node 2. So out dp of u, you can see that if there are more than one edges, you can use up the edge that provides the least value, but the child which leads to the maximum valued second missing element, that would still be available. So if the out degree of this node is at least 2, then the out dp of u would be equal to in dp of u. Now how do you compute f of I? So f of I just means that maximum of in dp of I, because the initial value is equal to I, or it can also be the maximum value of the out dp of any of the other nodes, right? Because remember that if you are standing at I, using one operation you can teleport to any of the other stations, and then from there you can travel any of the routes that you wish. So now it was clear what I needed to do. I just had to do this, populate this dp in the reverse order, and then compute this f of I and compute the sum for the remaining section. So now this is the code for this problem. First of all, we figure out the missing and the second missing element, and then we add an edge between them from missing to second missing element. Then I process all the nodes in the reverse topological order, and then in dp of I would simply be the maximum in dp of the children, and out dp of I would be equal to in dp of I, provided that there are two outgoing edges. Because if there is only one outgoing edges, then you will have to sacrifice that edge for that teleportation, and then you figure out the maximum value of that out dp, and f of I is nothing but in dp of I and the maximum value of out dp, and then this is the same sum formula as before. So now obviously I got a bit lucky in considering this out dp fact, because I see that a lot of people in the comment section missed this fact that you can teleport to a node, and that is why I did not face any issues for this problem during the contest. But if in future problems if I do get stuck on a problem during the contest, I will also tell you the approach that led me to nowhere, so that you can think about what to do and also what not to do. I will also link the code for this problem in the comment section, and if you do like the format of this video, do let me know in the comments.